Let's take a look at example 7, holiday spending. A survey by the National Retail Federation found that women spend, on average, $146.21 for the Christmas holidays. Assume the standard deviation is $29.44. Find the percentage of women who spend less than $160. Assume the variable is normally distributed. We want to be able to use our normal distribution to calculate percentages or probabilities. So let's first draw a table. I know I don't have a whole lot of room here. This is where section 6.2 starts. Like in the previous part of our lessons, let's graph. I have my mean here in the middle, and it tells me I have women that spend an average of $146.21. So there's my mean. I have a standard deviation, $29.44. And I want to find the percentage of women who spend less than $160. So I'm looking for percentage, but percentage is equivalent in our class to probability, which is also equivalent to area under the curve. So I want to know x less than 160. So remember here on my graph, this horizontal line is a number line. X is 160. Might sit somewhere here, but it's definitely going to be to the right of our mean. Less than 160 means we're looking at the area to the left of 160. I need to know what this area is underneath that curve. So again, this idea of percentage, it's the same as probability, it's the same as proportion, and it's the same as the area under the curve. All of these words are interchangeable in statistics. And so I'm going to use technology for these problems. I really want you to consider working with Excel or Google so that you become more comfortable with it. We will need Excel and Google very much in upcoming chapters. So go ahead and start getting used to working in them now. If you've taken a statistics class previously, and you have a graphing calculator, don't pull that graphing calculator out. If you've taken it before and maybe your instructor let you use tables, try not to use tables for these next sections. If you have no idea what I'm talking about for either of those, that's okay. Let's use technology. So here, x is less than 160. When I'm working with the technology, the formula gives me the area to the left. Just like our binom.dist function did in chapter 5, when we put true instead of false for that last conditional argument. We put true, we get area to the left of the number that we're given. The same thing happens with our normal distribution. Okay, so I'm going to write out what my command should be, and then we'll input it into our technology. So norm.dist, we'll put in our x value 160, our mean 146.21, standard deviation 29.44, and then for our normal distribution we always use true. Using the false takes a little bit more advanced statistical knowledge than what we're going to cover in our class. So for normal distributions we only ever use true. So x, mean, comma, standard deviation, comma, and then true. And if we hit enter, we get 0.68025, 0.6803, which would give us, if we change that decimal answer into a percentage, percent per 100, I get 68.03%. 68% of women spend less than $160. Now this should make sense because half of the women are going to spend $146.21 or less. So since 160 is more than 146.21, we'll pick up a little bit more than 50%. So having it 68% is a reasonable answer. Let's take a look at the next one. Example 8, emergency response. The American Automobile Association reports that the average time it takes to respond to an emergency call is 25 minutes. Assume the variable is approximately normally distributed and the standard deviation is 4.5 minutes. If 80 calls are randomly selected, approximately how many will be responded to in less than 15 minutes? Let's label what we have. Average time is 25 minutes, so I know my mean is 25 minutes. Standard deviation is 4.5 minutes. 80 calls are randomly selected. Approximately how many will be responded to in less than 15 minutes? This question is a little different because now we're asking a number, not a percentage or proportion. Remember that the normal distribution returns a proportion. So we need to find the proportion of calls that will be responded to in less than 15 minutes. And then consider how do we calculate how many of the calls will be responded to. Let's start out with our graph. We'll put our mean in the middle, 25 minutes. Less than 15 minutes. 15 is going to be over here on the left of 25. So we should end up with a proportion less than half. Remember, the 25 would split the graph in half. So we have something less than half, 15 to the left. So my proportion of calls, I can calculate using the normal distribution. So norm.dist, 15 is my x. My mean is 25, my standard deviation is 4.5, and we always use true. And I'm picking 15 here because the x value has the same units as our mean and our standard deviation. Our mean and our standard deviation have minutes. And so this 15 minutes here, that's our x. Let's find the proportion of calls that will be responded to in less than 15 minutes. And these functions, even though I'm using Google, they are the same in Excel. Norm.dist, 15, 25, standard deviation is 4.5, and we always use true. And we hit enter and we get 0.013. Now my graph is not drawn to scale. Just keep that in mind. Our graphs are never really drawn to scale. We get relative relationships between the numbers. I know I have to be less than 50%. Sure enough, I am. I get a 1.3% proportion. So now, this is my percentage. This is my percentage. I need to know of 80 calls, how many of them would be responded to in less than 15 minutes. So this will be a multiplication problem. We really want to know 1.3% of the 80 calls, which would be 0.013, so 1.3% times 80 calls. We get about one call. So one call would be responded to in less than 15 minutes.